Essentially, we are a group of students from different schools across the country that are dedicated to inspiring innovation and leadership in earthquake engineering. Our organization is made up of 3 targeted subcommittees: research, professional, and outreach. Through the subcommittees, we aim to engage and empower the earthquake engineering student community across peer institutions and beyond. Our team currently consists of 14 officers from across the network who work tirelessly to make a significant impact. We regularly host research and professional seminars, and we recently just launched a Pathways program that aims to connect undergrads and grad students who are interested in studying earthquake engineering. So whether you are interested in research, professional development, or outreach initiatives, we have something for everyone. If you have any questions about PSC and our programs, please don't hesitate to reach out to me or any of the other officers that are here today. So now I'm turning the floor over to Franco, who will introduce the speaker today.
Yeah, I think it will be me that I present him. So hello, everyone. Thanks for joining today's seminar. I have the honor to introduce today's presenter. So John Hooper is a senior principal and the director of earthquake engineering at Magnusson Clemensich Associates, a consulting structural and civil engineering firm in Seattle, Washington. He received his bachelor in civil engineering from Seattle University and a master of science from the University of California at Berkeley. John has over 40 years of engineering experience in the fields of renovation, earthquake engineering, and structural analysis, and has been involved in the majorities of NKS performance-based seismic high-rise design over the past 20 years. He is the chair of the Building Seismic Safety Council's NEHRP Provisions Update Committee, past chair of the American Society of Civil Engineering ASC 7 Seismic Subcommittee, and a member of ASC 7 Steering and Main Committees. He also serves on the American Institute of Civil Construction, TC3, TC5, and Committee on Specifications. So welcome, John. We're excited to see your presentation.
Great. Thank you all. And thank you, Student Council, for having me. I'm going to go ahead and share my screen, and we'll jump right into it. Again, a pleasure to be here. I want to talk about performance-based design. That's as was Gustavo just presented. That's what I've been doing a lot of my focus in both the work I do at Magnuson Clemensich Associates and in all the code stuff that you just heard me work on. I've been doing that for quite some time. So some of you may have already seen some of this before, but I want to put it into one big package about where we started and where we're heading, and at least in my opinion. Let's see. Okay, what is performance-based design? It's really simply an approach to do one of two things. One being to get a building that performs better than what the building code requires you to do. You want to improve its performance and make it more resilient, or whatever the case may be. But what we have found in practice is the second bullet, and that is performance-based design is typically used for buildings that don't meet the code regulation in one way or another, or in a few ways. But using performance-based design, you can show that you can get equivalent performance to that of a prescriptively designed building. So it meets the code, but you don't follow all the code rules. And by and large, and there's been hundreds and hundreds of these buildings designed in the last 20 years, it's because of the bullet number 2. We want to do something that's outside the code and prove that it works. Now I'm going to talk about generically performance-based design before I get into both seismic and wind. But without research and the work that you students do, and the students before you and before those students, we wouldn't be where we are today. And research breakthroughs, here's 3 different research items, if you will. The seismic one, that's a UC San Diego shake table. Without that, we can't really prove how well our designs really work unless you can shake it on a table to a full-size condition. Then we have the wall of wind in the center one, which allows us to really study wind and its effects in a much more robust way than we ever could before we had that down in Florida. And finally, the one on the right, the NIST fire testing facility that allows us to do full-scale testing on assemblies of structures and floors and columns and beams, et cetera, that allow us to really understand and really give a good feeling for how what we do analytically can be proven out with experiments, which is really important. In addition to the research that happens at universities that and NIST that we just saw, there are documents that have been developed with a lot of people involved in these various initiatives to put together best practices, and so that we can kind of do it in a similar way. It's not a code, but it's a guideline. The one on the left is the one for seismic. There's one of two that are out there. This is what was produced by PEER, the Pacific Earthquake Research Center. The latest version is 2017. And this guideline is for performance-based design of tall buildings. So specifically for buildings that are like 240 feet or taller, here's some guidelines about how to do that well. The one in the middle is fairly new. It's a couple of years old. It's performance-based wind design. If we can do it for seismic and we can take advantage of some analysis techniques, et cetera, for seismic, why shouldn't we do it for wind? And that's what we've done. And again, ASCE, the American Society of Civil Engineers, put together this document. Again, best practices for dealing with performance-based wind design. And the one on the right is performance-based structural fire design, and allow us to do more in the fire world. Specifically, I'll show it in just a second, using ASCE 7-16 as the go-by or to go to relative to performance-based fire design. Of all these three, the one that is most mature is seismic by far. We've been doing that for over 20 years. Both wind and structural fire are fairly new, and they're just beginning to be implemented in practice here in the United States. What is a basis, though, that allows us to do performance when we say equivalent to the code? And here for performance-based seismic design, what is in ASCE 7 is the performance objective, stated very directly. It's a low likelihood of system collapse subjected to risk targeted maximum considered earthquake shaking. What is low? The table on the left shows for risk category 1 and 2 buildings, ordinary buildings, ones we sit in pretty much every day, there's a 10% probability of collapse given MCE subbar shaking at the site. That's low. That's what we define as low. And as the buildings become more important, like risk category 4, which represent essential facilities, that number drops at 2.5%. And the table on the right is for a conditional probability of anchorage failure that could cause members failure in seismic. We don't really target that directly. We really target the overall system performance for seismic. Okay, now for wind, it's a little bit different. For wind, the performance objectives are for members and connections. Again, this table is in ASCE 7, table 1.3-1, where we target the probability of failure and the beta, the log normal distribution between the demand and capacity curves, a beta of 3. So I'm kind of circling this portion of the table under risk category 2, and that's kind of the target area that we're aiming for. But this is for member and connection. So wind does it differently. It's not a system-wide evaluation. It's a member and connection-based evaluation. At least for now, that's going to be changing down the road. And then finally, the overview for fire is based upon a conditional reliability of system, again, back to the system, assessment of ASCE 7 load combinations shown there. Those are for extraordinary loads because a fire is an extraordinary event. In the lower right-hand side of this image here is the important difference for fire. It's about the fuel load, how much fuel can burn, how long am I burning? You can see two extreme conditions. One is a bare office, and next to it is my desk. It's not quite that bad, but it could be. And the fire hazard and the fire fuel load is quite different. And we look at conditional limit state probabilities they see in the table on the lower left about what kind of fractal that we're trying to design for and the low limit of probability of failure. So that's kind of an overview, high level of both seismic, wind, and fire. Now I'm going to go back and go through in quite some detail on seismic, because that's the area that I work and live in every day. And we'll walk through this with you. The first one I have before me is the PBSD process. This could be for any performance-based process. It's very simple. You select your performance objective. What are you trying to achieve? You do a design, preliminary to see and get something set up. You create a model and assess its performance. Do the members meet the performance criteria? Does the overall building meet the performance criteria for global response? If the answer is yes, that initial evaluation, then you're done. If not, you revise your design until you deem that design to be acceptable. This is the most simple flow chart that you'll ever see, but it's truly the backbone or the framework for what we do in PBD, both seismic, wind, and fire. What are performance objectives? And it's very simple, a combination of an earthquake ground motion, usually termed in percentage of exceedance in 50 years. Typically, our number is 2% in 50-year ground motions, although there's a lot more detail to that I won't get into. And assign to that a performance level. And so different levels of ground motion have different levels of performance. Combine the two together, you get a performance objective. Let me show you what that means. Here is a classic representation, classic cartoon that we've been using for decades about these performance levels and the associated shaking level. A building that you all are sitting in today, and I am in my office, we're operational, the one on the left. Lights are on, everything's just fine. But if a frequent earthquake happens, what we want all buildings to perform like is they have immediate occupancy capability, meaning you can stay in the building, you're sweeping up some tiles, you're putting books on the bookshelves, things like that. But you're ready to go in the building shortly thereafter the event. That's a frequent earthquake, maybe a 50-year return period on that thing, kind of that range. The next one, life safety, it's called intermediate earthquake. That's really our design earthquake. And so our design earthquake, you can see by the cracks in the masonry there, we expect structural damage because that is the structural fuse that dissipates the energy from the shaking that the building feels. But and the lights are off because the power may have gone off, et cetera. And what the intent is here that everyone gets out fine. There might be minor injuries or so, but the building has a margin against collapse, a pretty healthy margin about not collapsing. The next performance level we describe as collapse prevention. This is right before the building wants to collapse and pancake or sidesway collapse. This is the kind of performance we try to target not happening using or witness to a very extreme rare earthquake, the maximum considered earthquake. That's the kind of performance that we are trying to guard against, right? Collapse, so that we don't want to kill people. You might get injured, but we want to minimize a whole building coming down. Here is the same kind of information shown on a building performance matrix. There's three lines go diagonally across the matrix. The upper right one is called, for ordinary buildings, risk category 2. If you concentrate on that line, there are 3 dots. And the most important dot there is what we target, again, is a 10% probability of collapse given MCE, so far as shaking. That's what we really are checking. The rest are inferred for risk category 2. And for the risk category 3 and risk category 4 buildings adjacent, that these lines start to shift over at the bottom row, the maximum considered earthquake row, the performance level shows improved behavior, improved performance. And you see that as this line goes up. So this kind of shows you in one quick matrix what we target, what the building code targets when we design for different risk category type structures, given different levels of ground motion you see here on the left of the matrix. We can look at the same information though, assuming a pushover curve. I assume most of us here on the call have thought about and been required to calculate a pushover curve, where you basically say, I have a building, I'm going to keep pushing it laterally, displacing it to the right, and assessing how it's performing as I push it. So thinking about that as an intensity of earthquake shaking, as I go up this curve, I'm still remaining elastic. Therefore, I have operational performance, like we're all sitting in our buildings or office or homes with everything's going just fine. We're in the elastic regime and nothing's happening and everything's elastic, all is good. You keep pushing, and all of a sudden you get a little bit of damage, a little bit of non-structural damage, etc. You have a tiny bit of non-linear response. There's a softening of your structure slightly. And so as the deformation increases and the demand from the earthquake increases, you start to see a little bit of yielding. You keep pushing the curve, push, and get all the way over to a life-safe performance level. Again, this would be at the design earthquake, so you're increasing the deformation quite a bit. You're increasing your basure or the force in the building quite a bit, but you kind of peaked, right? You have the flat portion of the pushover curve and life safety, that your design earthquake type of situation. But there's a margin, that's the key here, a margin against the next performance target, which is collapse prevention. So you have a margin so that, again, minimizing the chance that lives will be lost. And collapse prevention, again, is that MC shaking. It's right before it loses all strength and comes over. Again, minimizing loss of life and injuries at that event, and that shaking is associated with, again, that maximum considered earthquake kind of movements. So hopefully that performance information is clear enough, but that's important to know. That's what we target in our building codes. That's what most countries around the world target. We're shifting in that regard, but that's kind of where the world is at today. So what is it and how do we do it? And this is kind of an important discussion here. What we start with is member behavior on the upper left. We need to know how buildings deform, not just in the elastic range. That's easy. It's really in the inelastic region. So we understand how it performs when things start to crack and fracture, et cetera. That goes into our model. We create a three-dimensional nonlinear model, and we shake it with an earthquake or a series of earthquakes to understand how much damage might happen. Once you understand how much displacement occurs, how much acceleration, et cetera, in the building occurs, then you can ascertain how much damage could be in a column or beam, et cetera. What we try to do then with this information, though, is we try to target our model to be able to predict what the lab tests are showing us, whether the lab test is of a single column like you see here, or a shake table test like we have at UCSD, so we can kind of corroborate the model with physical testing. Once we have that kind of dialed in and we feel comfortable that we're close, that information flows right into this, what is our acceptance criteria, or the term I like to use, our backbone curve, that describes the performance characteristics of the various elements in the building. So what we try to do is, this is a loop. Once we have this information, we then change the member information, and we go back and continue to improve our process, mainly based on this testing that we see at the universities, both the United States and around the world. Okay, with that, why do we do this? And I mentioned it briefly before, and I'll be very discreet or distinct here. In the United States, new systems that are not recognized by ASCE 7, if you don't have a system that's in the standard, you have to do something different. You have to prove that it works. The second bullet is buildings with structural heights over 240 feet. You exceed the height limit that ASCE 7 has for certain building systems. And lastly, steel buildings greater than about 100 and 160 feet. There are excessive code prescriptive column axial demands that are required by AISC. And those demands are much more than the earthquake will generate. So we can save money. We can be more efficient in our designs when we look at steel buildings. Let me give you an example here. Here is a building I sit right next to here up in Seattle, Washington. It's called Rainier Square. It had a new system, composite plate core wall system with coupling beams. It was new at the time, and so we put it together. It is now a new system identified and codified in ASCE 7-22. Its name branded by AISC is Speed Core because it goes up really fast. And this building had a complexity of not only the composite plate shear wall core, but also had outrigger systems halfway up the building along each of its major lines, and an outrigger and belt trusses to help tie this all together at that level to help stabilize it for overturning. So this is a new system. PBSD is required because it's not in the standard. You have to prove that it's going to perform as intended by the standard. Here's examples of buildings over 240 feet. Generally speaking, these are concrete office or residential towers for which the core wall itself, that's kind of where all the elevators are and stairs, et cetera, is the lateral system. You don't need an extra or another backup moment frame or anything like that. You rely solely on the core wall system. If it gets too tall, you can see the building on the right. This is a building in San Francisco where we need to do 2 outrigger levels to help stabilize the overturning ability in the weak direction. So that's another why you do this, is for buildings that are too tall. And finally, here's 2 examples of braced frame buildings. These are buckling, restrained, braced frame buildings. They're over 240 feet, so we would have done a performance-based design anyways. We would have done it for columns only, but we had to do it for the entire building. And what it allows us to do is, and if you can look carefully at the renderings, the braced orientation and where they sit, et cetera, the architect has a lot more freedom to look at and provide the braces the way they want it to look. And we can analyze and make the design work using performance-based design approaches, because the code really doesn't recognize some of these brace layouts. And so we did do something else, and then this technique allows us to do and come up with designs that meet the performance objectives that we're trying to target. Again, how do we do it? I mentioned the peer TBI guidelines. This is written by the Peer Center. There's an alternative method for the Los Angeles region. It's a very similar document. They're almost the same. They're like 90% the same. This one on the right, the Los Angeles one, is updated more frequently. And so they're keeping up with the technology changes in a little bit more robust way. But these are documents that give us, and equally importantly, the building officials and the jurisdiction confidence that what we design and provide is going to work and be equivalent performance to the code itself. How do we do it? We start on the left with the red line you see is a target spectrum. That is a uniform hazard spectrum for those that know about ground motions. We have 2 other spectra there. There's scenario spectra 1 and 2. I call them conditional mean spectra for both short and long period. Whichever target spectrum you choose of the 3, and sometimes 2 out of the 3, once you have that defined for your site at MCE sub R shaking, then you select and scale ground motions who have the target on average to be greater than or equal to the target spectrum you see on the left. So that's what you see on the right. Here's a bunch of ground motions. There are 11 of them. That's what the standard suggests we do. And that's what we will analyze our building with, those ground motions. We'll shake our building with those 11 selected and scaled ground motions. And here's the nonlinear models. As simple as that. There's various tools out there. In the United States, most people today use Perform 3D. We have actually at MKA moved away from that. We're using ETABS nonlinear for our work. And there's a detail of why we do that these days. And we just model all the elements, and with all their nonlinear behavioral properties, their backbone, acceptance criteria, information, et cetera. And we take those ground motions and we shake it, and then we ascertain whether or not the members can withstand the demands that the shaking provides. And here's a result of a building. This is one in San Francisco. This is Salesforce Tower, the newest, tallest building. It's not that new now, but it was a while back. Again, a performance-based design tower. And here's a couple of simple metrics about how it performs. On the left is the overturning moment. About the x-axis, the center diagram is the forest shear wall in the y direction. And then on the right is the story drift along the y-axis. And you'll see that on the right one, you'll see 2 different dashed lines. These are the 2 acceptance criteria. The one I'm pointing to is the average limit of 2.4%. Both of these solid lines here are well below that. For any one ground motion, this dashed red line is the target acceptance criteria, and these dotted lines are maximum ground motion deformation, and that too is less than the acceptance criteria for global story drift behavior, which is one of the important criteria that we have to check the response for. And the other aspect of that, if you look at the story drift on the left, it's the same plot I just showed. The one on the right shows a strain in the reinforcing steel in the core wall. We model the rebar and we look at this and we measure, they're made out of fibers, and we measure the strain in the rebar. And then that's the purple plot on the right. The green plot on the left is the compression fibers that represent the concrete. And the dashed lines are the acceptance criteria. And even though the purple line at level 52 shows we're getting close to this green line, that's not our line of acceptance. Our line of acceptance is well beyond the page. That green dash line here represents 3 epsilon yield, 3 times yield of the rebar, well below its capability of going up to 10 to 15 epsilon yield before it fractures. So we're well within the range of behavior, both in compression and in tension for the rebar and concrete in the core wall for this building. The elements that do the energy dissipation are the coupling beams. Those are the beams above and below the door openings in the core wall. What we use is we do verification testing of our historic model that we put in our analysis routines and compare it to real tests. The one on the left are tests of diagonally reinforced coupling beams done at UCLA. And we make sure that our nonlinear behavior or historic behavior is consistent with the testing and close enough. The one on the right, the historic behavior there is for steel coupling beams, again, tested at UCLA. So we have different models depending on whether it's a concrete coupling beam or a steel coupling beam encased in concrete. So we look very carefully, make sure that we can verify our model against physical testing, like I mentioned earlier. The dots here on the middle acceptance criteria for the diagonal beam rotation, you can see that we're well under 1%. If you can see that zone here, much less than the acceptance criteria here at right around 5% rotation. We're not nowhere near it. We're well below it. So that's a good thing. The one on the far right is the steel coupling beam rotation. And there's a little bit more rotation on steel coupling beams because they're stronger and they take more demand. And so we're getting closer to the acceptance criteria, but we're still well within the acceptance criteria for the coupling beams. I will wait to answer questions, Gustavo, at the end, but yeah, I can answer that there. Yeah. Okay, I'm getting questions. I just want to make sure I check and see. Okay. Before, though, we're done with all this, and before the jurisdiction will say, yeah, go ahead and build it, your design is adequate, appropriate, etc., there's always a peer review process that is made up of experts that are not within your firm, colleagues that are doing this work in their own firms and different firms around the country. And they look at your design from beginning to end, and they ask a lot of questions, and they sometimes very hard questions that help to improve the design that the engineer of record is designing. And once all that discussion is over and you go through all the different comments they ask and all the responses that the design engineer responds back with, then the review process is successful when they approve it. So the peer review process is essential and jurisdictions require it. ASCE 7 requires it as well. It's a process that is required to be done. So that's what we've been doing for about close to 20 years now, and it's been done by dozens and dozens of firms, both here in the United States and abroad. And this is being used extensively in Southeast Asia as well, by both firms that from the United States that work there and by engineers that work in the Southeast Asia doing their own performance-based designs. Okay, here's the future, but the future is actually now as well. And this has taken some time to develop and why I called it the future. We were talking about qualitative performance like life safety, collapse prevention, et cetera. Can we quantify it with metrics that owners have a better chance of really understanding? Can we talk about what is the percentage of replacement cost after an earthquake happens? What might be the casualty rate? How much downtime might I have after an earthquake happens? How much time will I be out of the building? So this effort started in about 2000. The process of developing this information started in 2001, over 20 years ago, and evolved into what we call the FEMA P-58 methodology. What is that all about? It's a methodology that says, given ground shaking information about what kind of intensity I want to evaluate, I then evaluate the structural response of the building. How much does it deform and story drift? How much does the floor accelerate? And how much is the floor velocity? Because different things have different sensitivity to damage. And once we understand that, we can determine by developing what we call fragilities, how much damage might elements within the building feel given the story drift from the shaking or acceleration or velocity. Once we can pair those two up, aggregate that damage throughout the entire building, then we can estimate the repair cost, the repair time, and the casualties, and also unsafe placards or red tags. So that process of FEMA P-58 marries in the damageable elements within a building to the level of shaking that the building feels and estimates and can aggregate these losses that we're talking about. So this methodology was first released in 2012, so it's been quite some time. Wasn't used in 2012 very much. I'll tell you that right now. It's only starting to be used. And it does what I just said. It quantifies, at the key, not qualitatively, it quantifies building performance as probability of casualties, repair costs, repair time, and unsafe placards. And in 2015, we added environmental impacts, global warming potential metrics, so we understand how much CO2 is being affected by the losses due to earthquake shaking. How do we do this? It's simply by creating a different type of building model. It's called a building performance model. This is not an analysis model where you shake it and it's not like SAP or whatever, ANSYS or LS-DYNA or OpenSeas, whatever you guys use for your analysis. But this is putting in all the different elements in a building that is damageable. And damageable that, given shaking, story drift, et cetera, might break or fail given that shaking. This building performance model example shows windows in the upper left and cladding that goes with it, piping on the upper right, the structural components on the lower right, in this case, beams and columns, and partition walls. And it also includes ceilings and mechanical equipment and all the things that can be damaged within a building. And each of these components within a building have these fragilities that assess how much damage these might incur, given a level of story drift, floor acceleration, or floor velocity. So once we know that information, these fragilities can then help us identify how much damage there is. And from that, those fragilities also provide the consequences associated with how much does it take to repair it, how much cost it does to repair it, et cetera. So what we did as a follow-on to all this work in the methodology, this was about 3 or 4 years ago now, if we have this methodology and we design a code-conforming building, what do we anticipate its performance to be like on average in general terms? So what we have here is a table. This is for a risk category 2 office. The repair cost shows here is 10% given the design earthquake, and the repair time 45 days on average for an office building, regardless of height. That same general response for the MCE shaking, the repair cost would be 30% of the overall building cost. Repair time would be 150 days, almost a half a year, et cetera. So we, in very general terms, provide this information. It makes a big difference what kind of system you're talking about, whether it's a concrete shear wall system, a moment frame system, et cetera. But this is kind of looking at all of the results and kind of give a general response or generalized performance expectations for any code conforming building. So that's what we were targeting. That's what we're getting on average today. Well, that might not be good enough. Those numbers, if you look carefully, are quite substantial, especially with regard to repair time. There's been an effort underway for several years now is what happens if earthquakes happen in a major jurisdiction, major area, just like in Turkey, it happened a couple of months ago. How do you get back to functionality? Assuming that you don't have a bunch of collapsed buildings, how do you take these buildings that are damaged and how long does it take to actually get back in them? We define 3 functional recovery performance levels. The first one is reoccupancy. That is the ability to get in the building and start to do repairs and take out your belongings, et cetera. You can't stay there, but you can just be in there and start doing repairs, et cetera. But you can't use it yet. The middle cartoon shows functional recovery. That is, the building is repaired enough that the intended function of the building can be redone again so that If you're living there, you can live in there and have a reasonably inhabitable place. If you work there, you can do your work, etc. But it's not pristine because you still may have cracks in the wall. Ceiling tiles may be dislodged still, etc. It's not perfect. The last cartoon on the right represents full functionality. Everything's perfect, back to normal. And it's like the earthquake never happened. So that's the kind of thing we're looking at, figuring this out so that we can provide a different performance level than just how safe is it, and make sure that people come out uninjured, hopefully, but how quickly can we get people back in the buildings to use them again? A different thought process about dealing with that. What is functional recovery? It's a post-earthquake performance state in which a building is maintained or restored to support the basic intended functions associated with the pre-earthquake use or occupancy. And I just try to say it in words, and here's the actual definition that we use in the process of doing so. And then to what level of reliability, though? So here's some questions that we're asking right now. It was mentioned that I'm working on the Building Seismic Safety Council Performance Update Committee. I'm the chair of that group, and we're looking at this functional recovery performance direction and looking at it very detailed and trying to answer these questions. And once we answer them, then we can come up with the answers. So we're trying to ask, to what level of reliability should we target these performance levels for functional recovery? For what level of ground shaking? For the MCE shaking, for the design earthquake shaking, or some other shaking? Again, we're right in the middle of doing that right now as I'm speaking to you today. So how are we getting there? Well, we're getting there by the following. We've taken that FEMA P-58 methodology and we've extending it to deal with functional recovery, as the title of the slide shows. It's called the FEMA P-138 methodology. Again, it's just an extension of what the other one was, looking at functional recovery directly, where the 58 methodology was released here. The last bullet is what we're really targeting with FEMA P-138, and that is functional recovery time estimates. And we're doing that right now. We're nearly done. I had a meeting on it this morning. We just got done at noon. We're making great progress. We hope to have it done by the end of this fiscal year for FEMA, which is end of September. And we have a working beta version of it now, but it's always tweaking it here and there. For the intent of helping answer those other questions, we need a technical tool to be the foundation of making those decisions. And this is the methodology for which we're basing our approach on. Why are we doing this? This methodology is assisting in developing functional recovery framework, establishing the objective, like I just mentioned, establishing the design criteria, which I just mentioned, that we need that background information. And what will this result in the end is potentially model code provisions, although I hope they're only guidelines. At least initially, I don't want to go too far, too fast. Technical standards can be developed around this, and at some point in the future, likely that will happen. It also allows communities to do some interim provisions or requirements if they so choose that they want to have better performance than just a safety goal. If you want to have a functional recovery goal, this approach will give it to us. Okay, with that, I'm going to shift to the next piece. And that is, if I get there, wind. Just a brief discussion on wind. Again, this is fairly new, and this is something that here at MK we've been thinking about for quite some time before we started to actually do it for real. Wind has a spectrum of performance criteria, not too different than seismic, but they are different. At the bottom left here, you see what's called pedestrian comfort objective, meaning with very normal wind that occur in a city around your building, you don't want the people to be uncomfortable walking in and out of the building. And that's a real important thing, that you don't have difficulty opening the doors, et cetera, in windstorms that occur every once a month up to or the 1 year recurrence interval. The next one for high-rise buildings, the human comfort objective, is really important. That is one that actually drives building design as much as anything else, is that for tall buildings, we can't have a building that accelerates so much at the top that people are uncomfortable staying in the building in a windstorm. then if that's the case, then they'd have to leave. If this tall building were their home, their residence, they have nowhere else to go. So you have to be very careful and make sure you target and get to occupancy comfort objective. And that recurrence intervals between 1 and 10-year wind return period pressures that come around. I'll jump up to the very second to the top. That's the strength wind objective. That is what the code does. When you do a wind design per ASCE 7, that's the strength design. You got to make sure that you meet all the criteria in chapters 26 through 31 of ASCE 7 to make sure that you have enough strength to make that happen. What we're trying to assess next, at the very last top thing, is what about collapse? We don't want that to ever happen in windstorm, of course, but we can, with the right tool, see what kind of recurrence interval wind speed will cause that to happen. And we want to understand the full spectrum of performance so that we can dial in better guidelines associated with performance-based wind design. Why are we doing it? This is an example of what we found, and actually this is in Southeast Asia, where we were having the design of a seismic force resisting system that was dominated by the wind demands, meaning the winds were so large that the elements that we want to provide ductility for seismic were stronger than we would want to have, because wind requires it, because they have to remain elastic. So these ductile seismic elements had to be strengthened for elastic wind loads. And again, the next bullet down, their ability to initiate yield is reduced and can be reduced significantly, and then drives the demand on the elastic responding elements because the ductile element, the fuse of the building, is too strong. So if we could get some relief and a little bit of nonlinear behavior due to wind demands, then and still perform well and still meet the targets reliability in chapter 1 of ASCE 7, then we can have a reduced size of members for seismic, and we have a better balance of a system, a better balanced building that perform both well in wind and equally well in seismic without overly being conservative and spending extra material, et cetera, in the building that you really shouldn't need to do. So we got the issue of this wind-induced demands that govern seismic design members. So a group of engineers and others got together and, as I mentioned earlier, created this performance-based wind design. The second version, just came out. It's coming out right now as we speak, volume 2. We've updated some things within it. And so it has in it this table that you can't read very well, table 4.1, performance objectives and acceptance criteria. It has all the different things we think about and care about. At the very top, occupancy comfort, operational criteria, and continuous occupancy type of performance lexicon and language. It's different than in seismic. It should be. It's different, and talks about different things between the seismic system, the wind system, the envelope, and components within the building. So a lot of thought, a lot of effort went in creating acceptance tables like this within this guideline that kind of provide the basis of our approach for wind PVD. Within the wind PVD document that I just showed, there are 3 methods of evaluating this continuous occupancy performance evaluation. That would be collapse prevention in the seismic world. But there's 3 methods. The one on the far right, method 3, is what academics are working on trying to do right now, being led by the University of Michigan. I was just there, as I mentioned earlier, a couple of days ago. And so it deals with nonlinear response history analysis. But the key point here is the box in the middle. This is a fully coupled reliability assessment, meaning once you put all the wind responses in and you see the nonlinear response of the building, you will determine what the reliability is at the end of the analysis, component by component, by story drift, and by collapse. It does it all within one full analysis in one big technique. There's a lot of analysis that goes on. It takes a long time, but we're heading in that direction. And sometime down the road, it's getting very close to being fully functional to be able to do this fully coupled reliability analysis. Method 2, this comes from the seismic world. This is a conditional probability reliability assessment, as this middle box here indicates. It follows really the approach that we've done in Seismic for decades now. And we've created an appendix that allows us to use a conditional approach to sizing and evaluating the performance of a building to wind. The one that we have used though on buildings, and actually I'll show you in a second, is method 1, which is basically you do a linear elastic evaluation. You keep the yielding of the ductile elements to a low level. Then you do nonlinear response history analysis of wind demands, critical wind scenarios. And once you get through with all that, when you check the members and drifts after that, do you meet the acceptance criteria? If you do, then you met the performance-based target for wind. That's the method that, again, is the most straightforward today. Here's a building in Austin, Texas, for which this building got a permit. It's under construction right now. And we're showing you the model that, the nonlinear model that was created for the building rendering you see on the left. And it's a series of concrete shear walls is a major system. It has some outrigger walls for helping for stabilizing overturning. The coupling beams are the element, again, that does, if there is inelastic action, it's going to be in the coupling beams, limited, of course, to what it can do, etc. And so we do that. What's the method? Here's a step-by-step method. It's straightforward in the sense that you proportion the system, get initial sizing. Once you have the initial sizing, you send that model information to the wind tunnel testers. They come back and assess the comfort, occupancy comfort numbers. As I mentioned earlier, that's one of those key things you do. Next thing you do is you assess the drift to make sure you're not drifting too much, given those demands from the wind tunnel. Then you start to do then if this is a traditional design, you would just then do your typical strength design and you'd be done. What we do here is, next thing, we design for linear response history analysis, not just a static wind load. We do linear response history analysis and look at and see what the criterion is for the different components and make sure that we don't exceed the acceptance criteria for them. Once we get through and we feel past those values and acceptance criteria, then we build an enhanced nonlinear response history analysis. We conduct the analysis using the wind time histories from the wind tunnel. These wind tunnel time history are an hour-long windstorm. Those hour-long windstorms takes us 2 weeks to analyze per windstorm because there's a lot of data. It takes a lot of time to do the analyses. Then once you go through and you assess the peak demands, et cetera, and you can compare the acceptance criteria against those peak demands. And if you're successful, you're done, just like the initial flow chart showed at the very beginning. If not, you have to make changes to your design and do it again until you pass all the acceptance criteria for the nonlinear response history analysis for wind. So that's where we are for wind. That's where we are for seismic. I have about 10 minutes left. I'm going to then open, I guess, back up for questions. I'm going to stop sharing my screen. Student council, is that okay? I'm going to do that. So as we get questions, we can respond to them accordingly.
Yeah, thank you, John, for this great presentation. I'm going to read the questions one by one so everyone can know what the question is.
Great.
So the first question is, how do you model the speed core in the analysis in ETABS layer shell?
We did that one in Perform. That was before that, and we use fiber. Yeah,
okay.
ETABS, just so you know, we both use layered shells and ETABS, and we're probably going to go back to fiber models in ETABS nonlinear, because we can do both. And the fiber model in ETABS nonlinear is faster than the layered shell. And so we can do it both ways in ETABS, but Perform, we are using fibers.
Okay. So what do you think are the advantages or disadvantages from ETABS, Perform 3D, or OpenSeas if the nonlinear is done there?
Well, first of all, OpenSeas isn't done by the practicing engineering community because we don't know how to use it. All you students are very, very good at it, but we aren't. The graphical user interface doesn't exist in a robust enough way for at least us. So the primary reason, two reasons we went from Perform, which we used for over 15 years, to ETABS. First of all, three reasons. ETABS nonlinear improved over time. Initially, it wasn't good enough to do what we needed to do. Secondarily, Perform 3D was not being extended enough with all the new challenges we were facing. The most important challenge is vertical ground motions or vertical load effects. Perform was never written around that. It doesn't do vertical ground motions very well at all. ETABS can do that, and that can become very important when you have buildings that have large transfer trusses and sloping columns, where the building is affected by vertical load effects. Perform just doesn't capture it very well at all. And that's what drove us to looking at ETABS nonlinear. It can, now, OpenSeas is the best tool of all. We know that, but it's too cumbersome for us to typically use.
Okay. In your experience, do you get significant differences in the structural demands in the building when you use two CMS as target rather than a uniform risk spectrum, or is it about the same demands?
We get it's about a 10% less demands or more using in CMS versus uniform hazard, 10 to 50% less, generally speaking, especially for the short period effects that the higher mode effects reduce typically.
Great. So how this method accommodates an area in which 50 years have passed from the earthquake with the return period of 2,500 years and no earthquake has happened. It will increase the probability of a major earthquake in the short lifespan of the building, but PBD seems to have no way to accommodate that.
Yeah, the way we accommodate PBD for frequent earthquakes, we just assign a shaking, at least on the earthquake side, and same thing for wind. We'll assign a 1 or 10-year wind speed for service level. And so we just get a shaking and make sure that we're essentially elastic for that. For the safety check, the collapse check, we want to use a big event, a rare event, because the consequence of something bad happening is large, and we don't want that to happen. So the fact that the earthquake hasn't happened, it could happen tomorrow. Right? We use a Poisson distribution. We don't do time-dependent models for seismicity parameters, right? We use the Poisson distribution. So it could happen today, it could happen tomorrow, and it's the same risk for us.
Okay. Have there been any events in which a performance-based design building performed worse than expected?
Oh, probably not worse. The best analogy we can look at this, guys, is we've been using performance-based design for existing buildings for quite some time to improve, take an old building and make it better. So a lot of these techniques were initially founded based upon that. And generally speaking, what I've been able to see from my colleagues and everything, it's always shown an improvement in the behavior. Not, just to be clear, not a lot of the new designs we've done in the last 15 or 20 years have seen a big earthquake. So Mother Nature will tell us down the road sometime how well we've done.
Okay. Why the design codes and the PBSD method now don't take into account the resistance of aftershock earthquakes after the main earthquake? As we saw in Turkey after the 7.8 magnitude earthquake, lots of 6 magnitude earthquakes have been happening within the days after, and that damaged buildings.
That's a great question. Our building codes have never taken account the aftershock potential. I'm not saying it shouldn't. I'm not saying that. We've always looked at it as a major event, and that's it. And that's good enough. There's been research, and I'm sure some of you may have done some research in this regard. You know, how much reserve capacity do buildings have after a major shake? And we saw that in Turkey when we saw those horrific additional collapses that occurred after the fact due to aftershock. That we just haven't. It's not part of our performance target at this time. It might be, guys, in the future, but it isn't right now.
Okay. Do you plan to do training hands-on sessions on PBD and ETABS in nearest future?
No. Now,
Okay.
you mean the detailed teaching and training?
Yeah, I think that's what he meant.
What we do is what we've done already. We've published some papers about what we do, and so, but we won't. We just because everyone else does it their own kind of way, whether you use ETABS or Perform, etc. So, or for those that do end up going with OpenSeas.
Okay, what are the advantages and disadvantages of shell layer element compared to fiber section when simulation non-linearity for shear walls? Which method is more suitable for shear walls?
That's a great question because we're, as I mentioned earlier, when we first went to ETABS, we thought layered shell would be the better way to go. And it's fine, it works fine. And we validated it via tests. We take our shell elements, we build up our 5-layer shells and using different test results that compare how accurate our model is compared to it. And then it was taking longer to run than the fiber elements and perform. And I said, okay, why don't we just think about it? ETABS has a very similar engine than as does perform. Let's try to go back to fibers. And it turns out that we could model and with using fibers, it get pretty good validation or verification, I should say, with a test result. So we're heading towards back to fibers for ETABS because it gives you the same answers plus or minus less than 10%, but it runs quite a bit faster. And that, when you're talking a couple of weeks to run analyses, 10 or 15 or 20% faster is a big deal.
Okay. Says, going back to the software, if ETABS is preferred for the analysis, how would you solve the problem when 321 West 6th Street takes 1 month to run for PPWD? I don't know if that's a specific address.
Yeah, the problem, there's differences because remember, a wind demand is 1 hour long of shaking. Earthquake is 45 seconds. There's a big difference. It takes a lot longer. And the loading regimen is much different. You're loading each level with its own wind loading variation, where you're taking and shaking your foundation with a 45-second level of shaking. So it's the loading protocol is much, much different. And that's what causes it. Not the model itself, it's the loading.
Okay. What is your opinion about the robot structures in comparison with ETABS and SAP?
You know, robot software?
Yeah, robot structures, I think it's Autodesk.
Yeah, we don't use that. We did a long time ago, about 20 plus years ago, we used robot for a while and decided to move on from that. So not that it's not good or not, we just don't know. We don't know about it. So
Okay, and the last question, do you see any prospect of retiring prescriptive design approach and replacing it completely with PVD?
I think we will always have a prescriptive approach because if I'm designing a house, a residence, like there's a lot of people that design houses, they love to design houses. There's always a reason for prescriptive design. So that will never go away. What we want to have happen is we want performance-based design to be the preferred approach, and the prescriptive approach in ASC7 becomes deemed to comply. I mean, if you follow all these rules, you're deemed to meet the criteria in, again, chapter 1 of ASC7, but the underpinning should be first and foremost, performance-based design is number 1, but prescriptive design will always happen because of other systems. Anything that's tall here on the West Coast is all PVD now. No one does a tall building without doing PVD, and it has been done. PVD has been done for the last 10 years for anything tall and high seismic, but not for the short stuff. It's not worth it.
Okay, I think those were all the questions. Patricia, do you want to?
Yeah, sure. Thank you everybody for being here with us today. We appreciate your time, and thank you so much, Mr. Hooper, for being with us today. We really appreciate your insights, and we thank you for your time. You're a very busy man.
It was a pleasure. Great to meet the council and the rest of the people on the seminar. Hope you enjoyed it. Good luck with your futures. The future's bright. Okay. Take care.
Thank you.